All right, my name's Josh, and I'm going to be taking you guys through problem number 39 in chapter 3. Chapter 3 has to do with vectors, so this is a vector-related problem. The problem says that a radar station locates a sinking ship at range 17.3 kilometers and bearing a 136-degree clockwise direction from north. So I went ahead and I already drew that in. This is the 136-degree clockwise direction from north. So we started at north, 136 degrees clockwise. And then this is the magnitude direction of, or distance of the ship, 17.3 kilometers. And then from the same radar station right here at the origin, it locates a rescue plane with a horizontal range of 19.6 kilometers and a 153 degrees clockwise direction from north. So you count down clockwise again from north 153 degrees, and that puts you right here. And then the horizontal range of the plane is 19.6 kilometers. Also, since the plane is flying above the radar station and where the ship is located, it has a elevation, a vertical direction or distance of 2.20 kilometers, and that's going to be in the k-hat direction. So what we want to do first is write out the position vectors in component form of the boat or the ship, same thing. So what you want to do is write 17.3, which is the magnitude, sine of 136, which is its direction, that's in the I-hat, plus 17.3 cosine of 136 in the j-hat, plus 0 in the k-hat because it does not have any elevation. And you notice that I chose to use sine of 136 in this case for the I-hat direction because if you look at it like this, since it's coming from north, so you have to kind of look at the problem in a different way. See, if you took sine of 136 right here, you're going to get this direction, this going in the y direction in this view, but if you went in this view, it's actually the x direction or the I-hat direction. So that's why I chose sine, and the same kind of concept with the cosine. If you use cosine in this case right here, you're going to get this direction, which is actually the j-hat in this view. So sine 136, cosine 136 for the I-hat and then j-hat directions respectively. So we'll do the plane next. So its magnitude is 19.6. So we'll do sine of 153, which is its direction from north, in the I-hat, plus 19.6 cosine of 153 in the j-hat direction, plus 2.20 in the k-hat direction. That's its elevation. So part A of the problem asks you to find the position of the boat relative to the plane. So basically it's asking for the plane's view of the boat from up above. So what you want to do is just subtract these vectors. So that gives you 3.12 kilometers in the I-hat plus 5.02 kilometers in the j-hat minus 2.20 kilometers in the k-hat. It's all in kilometers. So what this does is it just gives you the plane's view of the boat. In this problem right here, it's the radar station's view of the plane and the boat. So when you just subtract them, it takes out the radar station's approach on it, and it just gives you the plane's view of the ship in this case, because it's the boat's position relative to the plane. And this makes sense because the plane looking down on the boat right here is going to give you a negative 2.2 kilometers in the k-hat direction because it's looking down on it. And if you draw in your I-hat, or this is your j-hat right here, and then your I-hat going across, it gives you the horizontal distance from the plane to the boat, not including the 2.2 kilometers up. It's just the horizontal. So in this case, the magnitude of the j-hat and the I-hat right here is going to be these two right here combine, and then the square root, or the squared, and then the square root of that, which gives you the horizontal distance. And what part B asks you to do is to find the actual distance up above from the plane to the ship. So it's kind of like a diagonal, basically the resultant vector of the elevation and then the magnitude of the horizontal direction, the I hat and the j hat. So it's this right here. And then if you look carefully, this is actually forms a right triangle. So you can redraw your triangle down here. So this is the boat, and then this is the plane. And then the plane is 2.2 kilometers above. And this right here, the magnitude of the I hat and the j hat is 3.12 I hat plus 5.02 in the j hat. And then to find the magnitude of that, you do 3.12 squared plus 5.02 squared, and that equals 5.91 kilometers. So now that you have the distance from the plane and the plane to the boat in the horizontal direction, and the elevation is 2.2, you can easily find this, which is the actual distance from the plane to the boat, the magnitude of this and this. So you just take what you did right here and just using these two numbers, these two distances. So 2.20 squared plus 5.91 squared equals, and the square root of that is 6.31 kilometers, and that is your distance from the plane to the sinking boat or ship. So that's the problem. Part A is this part right here. It's asking for the position of the boat relative to the plane, so the plane's view of the boat. And then part B is asking for the distance from the plane to the boat. So the tricky parts of this problem are realizing that the plane has an elevation, a k-hat direction. You have to take that into consideration to get the right answer. You use the k-hat direction right here with the magnitude of the I-hat and j-hat direction on the horizontal plane down here to get the final distance of the boat and the plane, which is going to be the diagonal resultant vector of those two. Also, another tricky part is going to be figuring out which direction to use as far as sine or cosine and of what degree. Like I said before, you're going to need to look at the problem like this to figure out that you need to use the sine to get the I-hat direction, and you need to use the cosine to get the j-hat direction. So sine I-hat, cosine j-hat, and that's basically it. This is problem number 39 from chapter 3.